Imagine the most important physical locations on Earth right now. I mean, we might be picturing the bustling trading floor of Wall Street or, maybe massive offshore oil refinery.
Or global shipping canals, right?
Yeah, exactly, shipping canals. But the real centers of power today are actually these totally nondescript, windowless warehouses humming with just an unimaginable amount of electricity.
Welcome back to AI Business English Daily. In the next 15 minutes, we'll unpack one important story from the world of AI, business, and technology and help you learn the English behind it.
And our mission for this deep dive is to explore the company building the components inside those windowless warehouses. We're looking at Nvidia. The core question we want to answer for you today is how this one specific company became the literal backbone of the economy for the AI era.
Right, and when we use the phrase backbone of the economy, we mean the foundational support structure that modern digital business relies on. It's much like how steel and concrete supported the Industrial Revolution.
Exactly. We aren't just talking about a chip manufacturer having like a successful financial quarter here. We are examining a massive platform shift.
A platform shift.
Yeah, which is a fundamental change in how technology itself operates. We are moving away from computers that merely execute pre-recorded software to systems that generate original intelligence in real time.
And to truly comprehend the magnitude of this platform shift, we really need to look at the financial realities. The scale is almost difficult to conceptualize. I mean, Nvidia recently reported their first quarter revenue for fiscal 2027.
The numbers on this are just wild.
They really are. They achieved a staggering $81.6 billion in revenue for just that single 3-month period. That represents an 85% increase year over year.
Wait, $81.6 billion in one quarter. Those are numbers we usually associate with the gross domestic product of entire countries, not a single technology company's quarterly earnings.
It is unprecedented, but the breakdown of that revenue tells the real story here. Out of that $81.6 billion, a record $75.2 billion came from data center revenue alone.
Wow, so almost all of it.
Yeah, almost all of it. And if you look back at their previous full fiscal year, fiscal 2026, their total data center revenue hit $193.7 billion. So this metric, data center revenue, which is the income generated from providing hardware and services for cloud and server infrastructure, is the absolute center of this story. Data centers are the engines driving this growth.
I have to admit, there's a huge disconnect for me here that we need to bridge. Not that long ago, if you asked the average person about Nvidia, they would tell you it was a company that teenagers loved, because they made graphics cards for video games.
Right, for gaming PCs.
Yeah. But today, they are designing these AI data center components that cost up to $3 million a piece. I read that a single server rack can weigh 2 tons and consume 200,000 watts of power. Like, how on earth does a consumer video game company pivot to becoming the chief architect of global industrial infrastructure?
Well, the pivot seems drastic from the outside, sure. But it follows a very strict technological logic when you look closely at how the hardware actually works. The foundation of this transition relies on a concept called accelerated computing.
Meaning using specialized hardware to speed up incredibly complex tasks, right?
Precisely. To speed them up far faster than traditional methods. For decades, the entire technology industry was built around the CPU, or the central processing unit.
The component we usually think of is the brain of a standard laptop or desktop computer.
Exactly. Let's break down how a CPU functions. A CPU is designed for sequential processing. You can think of a CPU like one incredibly brilliant mathematician.
Okay, one smart mathematician.
If you give that mathematician a highly complex logic problem, they will solve it very quickly. But they can only solve one problem at a time. A GPU, or graphics processing unit, operates on a completely different architecture.
So how does a GPU work in that analogy?
A GPU is like a massive stadium filled with thousands of elementary school students. None of them can solve complex calculus, but if you give all of them a basic arithmetic problem at the exact same time, they can solve thousands of problems simultaneously. That is parallel processing.
And parallel processing is mandatory for video games because of the sheer visual math involved, right?
Spot on.
Like, if a gamer is playing on a 4K monitor, there are over 8 million individual pixels on that screen. To make the lighting and shadows look realistic, the computer has to calculate the color of all 8 million pixels 60 times every single second.
Yeah, you simply can't do that sequentially. You need the stadium full of students calculating those pixels all at once.
Okay, that makes sense.
And that visual math is actually matrix multiplication. Nvidia spent over 2 decades obsessively perfecting this parallel processing architecture, really just so video gamers could have better graphics.
But then AI happened.
Right. Eventually, a profound realization hit the technology sector. It turned out that the exact same matrix multiplication required to draw millions of pixels on a screen is the exact kind of math required to power artificial intelligence and neural networks.
Because AI doesn't need one brilliant mathematician.
Yeah.
It needs to calculate millions of tiny data probabilities simultaneously.
Exactly.
So they basically accidentally spent 20 years building the perfect engine for artificial intelligence.
Yeah.
That is amazing.
It really is. And that realization allowed Nvidia to completely transcend the consumer desktop market. They began building the ultimate infrastructure layer for the modern internet.
The infrastructure layer, meaning the underlying hardware and physical systems that allow higher-level applications to function.
Yes. Because of this new infrastructure layer, data centers underwent a massive evolution. They are no longer just passive warehouses where companies store old email files or host website data. Nvidia transformed them into what they now call AI factories.
Calling them AI factories completely changes how you visualize them. Instead of manufacturing cars or steel, these factories take in electricity and data as their raw physical materials, and they literally manufacture intelligence.
It's a total paradigm shift.
But building an incredible factory doesn't guarantee you'll dominate the market. You can engineer the most powerful microchip on the planet, but if software developers don't actually know how to write code for it, your chip is essentially just a very heavy, very expensive piece of silicon.
How did they get the software developers on board?
Well, the software strategy is arguably the most crucial chapter in NVIDIA's history. While the hardware gets all the flashy media headlines, the software is what actually secures the business model.
How so?
To fully appreciate why, we first need to break down the AI lifecycle into two distinct phases: the training pipeline and the inference workload. Let's explore that division because I think people often lump all AI functions together. The first phase is the training pipeline. The term pipeline in business English usually refers to a sequence of processes. So the training pipeline is the intensive, upfront process of teaching an AI model from scratch.
That is a great way to frame it. The training pipeline requires gathering trillions of text documents, images, and data points and feeding them into a neural network so it can learn to recognize patterns.
Which takes a lot of time, I assume.
Oh, it takes weeks or even months of uninterrupted, massive computational power. If we use an analogy, the training pipeline is like a student studying for the hardest exam of their life. They are absorbing vast amounts of information and making neural connections.
Then the second phase must be actually taking the exam.
Yes, and that is called the inference workload. Once the AI is trained, it goes out into the real world. When you type a question into a chatbot on your smartphone, or when a self-driving car needs to identify a stop sign in a fraction of a second, the AI is taking what it learned during training and using it to infer the correct answer.
So that is the inference workload.
Exactly. And there has been a massive shift in the tech industry recently. The inference workload has officially overtaken the training pipeline as the dominant activity. AI is no longer just being built in a laboratory. It is being deployed to millions of end users.
Which completely rewrites the economics of the entire industry.
Yeah.
I mean, training an AI might take months, but it only happens once per model. Inference happens billions of times a day, every single day. So how did NVIDIA manage to lock in both the people building the AI and the people deploying it?
They achieved this by introducing a software platform called CUDA all the way back in 2007.
2007, that's really early.
Very early. Before CUDA, GPUs spoke a completely alien language compared to traditional CPUs. If a scientist wanted to use a GPU to calculate a complex physics simulation, they literally had to trick the GPU into thinking the math problem was a pixel rendering problem. It was incredibly tedious.
So what did CUDA do?
CUDA changed everything. It was a programming language that served as a universal translator, allowing developers to easily talk to NVIDIA's GPUs.
So they didn't just sell the physical hardware. They distributed the exact tools developers needed to extract value from that hardware.
And they spent nearly 20 years refining it. Because they started so early, millions of developers learned to code using CUDA. Today, billions of lines of global software code rely entirely on it. This created what we call a full-stack ecosystem.
A full-stack ecosystem, meaning a company provides every single layer of the technology.
Hmm.
The physical chips, the networking cables connecting them, and the software language running on top of them.
Exactly. And having a full-stack ecosystem creates something every business desires, which is incredible switching costs.
Oh, switching costs. In business strategy, a switching cost refers to the massive financial expense, time, and engineering effort required for a customer to abandon one vendor and move to a competitor.
Right. If a major cloud provider suddenly wants to buy cheaper chips from an Nvidia competitor, they can't simply unplug the hardware. They would have to rewrite decades of complex software code from scratch because their software only speaks CUDA.
Which acts as the ultimate competitive moat. Just as a physical moat protects a medieval castle from invasion, a competitive moat is a structural business advantage that protects a company's market share from rivals. Nvidia's moat is built on millions of developers who are deeply comfortable using their software.
It makes perfect sense why they are so dominant.
But I have to imagine this castle is currently under siege. The major tech giants, the hyperscalers like Google, Microsoft, Meta, and Amazon, they cannot be happy about paying huge premiums for Nvidia hardware while being locked into their software. Based on the industry data you're seeing, how aggressively are these giants trying to cross that moat?
They are mobilizing unprecedented amounts of capital to cross it. Current projections show that the major hyperscalers will spend a combined $660 to $690 billion on capital expenditures by 2026.
That is just an astronomical amount of money.
It is, and a massive portion of that is dedicated to AI infrastructure. They are highly motivated to escape this reliance on a single supplier. As a result, we are seeing a surge in custom ASICs.
Custom ASICs, application-specific integrated circuits. How do those differ from the GPUs we've been talking about?
Well, an Nvidia GPU is highly versatile. It can render a stunning video game, simulate global weather patterns, or train an AI model. But versatility comes with a high physical cost. An ASIC strips away all of that general-purpose functionality.
So it only does one thing.
Exactly. A custom ASIC, like Google's TPU or Amazon's Trainium, is physically baked at the silicon level to do only one specific type of math equation. It is completely useless for rendering a video game, but for running an AI inference workload, it is significantly cheaper and more energy efficient.
And energy efficiency is the entire game when it comes to the inference workload. If a company is processing 3 billion AI chatbot queries every single day, shaving just 1/10 of a cent off the electricity and compute cost for each query saves an absolute fortune.
Right? It dictates their return on investment, or ROI. Return on investment is the ultimate measure of profitability. It calculates the financial gain you receive relative to the cost you put in. Because the hyperscalers are desperately chasing a better ROI, they are designing these custom ASICs specifically to optimize their inference costs.
So the threat is very real.
Very real. Some analysts project that because of these custom in-house chips, Nvidia's market share for the inference workload could potentially drop to 20 to 30% by 2028.
Wow. So while Nvidia still effectively owns the training pipeline because of their versatile GPUs, the inference workload is becoming a fiercely contested battleground. But beyond just competing chip designs, there's a fundamental physical limitation affecting everyone in this space right now, isn't there? We're looking at massive constraints in the physical supply chain.
Yes, the physics of manufacturing are really catching up to the software dreams. The entire tech sector is facing a severe supply constraint.
A supply constraint occurs when market demand vastly outpaces the physical ability to produce and deliver goods.
Exactly. For AI hardware, the biggest bottleneck isn't just the processors, it's the memory. AI chips require a highly specialized, ultra-fast type of memory called high bandwidth memory, or HBM.
Because if you have thousands of GPU cores calculating data simultaneously, you need a memory system that can feed data into those cores fast enough so they don't just sit idle waiting for information.
Exactly the problem. But manufacturing HBM is incredibly complex. The memory chips aren't just laid out flat, they are stacked vertically, like microscopic skyscrapers of silicon, connected by microscopic wires running straight down through the layers.
That sounds incredibly difficult to build.
It is. This process requires highly specialized bonding equipment, complex thermal testing, and it takes up significantly more time and physical floor space in a fabrication plant.
I read that for the major memory manufacturers, producing HBM requires a 3-to-1 trade ratio with standard memory.
Yeah, that's right.
Meaning, For every one wafer of high-bandwidth memory they produce for an AI chip, they have to sacrifice the factory time and space that could have produced 3 wafers of standard DDR5 memory used in everyday laptops and servers.
And that 3-to-1 ratio is causing a ripple effect across the entire global economy. The insatiable demand for AI data centers is actively eating into the supply chain for traditional consumer electronics.
It's crowding everything else out.
Exactly, which is why we are seeing prices for regular computer RAM and storage drives surging globally. The demand for artificial intelligence is quite literally outstripping the physical capacity of our silicon fabrication plants.
This entire discussion really highlights how intricately connected the technology is to the underlying business strategy. I actually want to pause here and reflect on the language we've been using throughout this deep dive.
Good idea.
If you are a global professional or an English learner, you've probably noticed that the vocabulary surrounding AI isn't just about coding. It's about business architecture. The language of business is shifting to adapt to this new reality.
It is a fascinating evolution in corporate communication. The terms we've been unpacking today aren't just technical jargon. They are strategic concepts that define how multi-billion-dollar decisions are made in boardrooms around the world.
Think about how a modern strategy meeting sounds. 10 years ago, an executive might have simply said, "We are buying server hardware." Today, that same executive will talk about investing in the infrastructure layer.
Right.
Using the term infrastructure layer elevates the conversation. It implies you are building a foundational system that other software and services will rely on, not just purchasing equipment.
And when discussing market dominance, executives rarely just say, "Oh, we have loyal customers." They analyze their competitive moat and how to deepen it. They look at the full stack ecosystem they've built, evaluating how tightly their hardware and software are integrated.
Because the goal of that ecosystem is to intentionally create high switching costs. When you understand that switching costs include the agonizing engineering effort required to rewrite software from CUDA to a competitor's language, you understand why the moat is so difficult to cross.
You also hear a distinct shift in how companies categorize their daily operations. They don't just talk about running AI, they specifically differentiate between the training pipeline, which is the massive upfront investment in teaching the model, and the inference workload, which is the daily, real-time application of that model.
And recognizing that difference is critical for discussing return on investment. When a hyperscaler builds a custom ASIC, they are doing it because optimizing the inference workload is the only way to achieve a positive return on investment at scale.
We also discussed macroeconomic terms. We talked about a platform shift, signaling a once-in-a-generation change in how we interact with technology.
We labeled Nvidia the backbone of the economy, illustrating how their data center revenue is now a primary indicator of global tech health.
And we grounded it all in the physical reality of a supply constraint, driven by the massive demands of accelerated computing. When you master how these concepts interlock, you aren't just learning vocabulary, you are learning how to decipher modern business strategy.
The companies that understand how to navigate these specific concepts are the ones that will define the next decade of digital growth. Which brings us to the most important part of our deep dive.
Time for the takeaways.
Exactly. We've explored the history, the hardware evolution, the software strategies, and the economic realities. Let's distill all this complexity down to 3 core takeaways for you to remember. Takeaway 1 is the hardware foundation. Nvidia achieved its massive scale by recognizing early that the parallel processing used for video games was the perfect architecture for artificial intelligence. By transforming their gaming chips into the ultimate infrastructure layer, they successfully rode the biggest platform shift in computing history.
Takeaway 2 is the software defense. While the massive, powerful chips capture the public's imagination, software provides the long-term business defense. Their CUDA programming language created a deep competitive moat. By establishing a full-stack ecosystem that developers rely on, they generated astronomical switching costs that lock in their customer base.
And takeaway 3 is the shifting battlefield. The war is far from over. As the AI industry matures and shifts focus from the training pipeline to the highly lucrative inference workload, Nvidia faces intense new challenges. Tech giants are designing custom chips to lower their costs, and severe global supply constraints on specialized memory are testing the entire industry as everyone chases a better return on investment.
When you step back and view this entire landscape, it really forces you to reconsider how the modern world operates. If we accept the premise that these new AI factories are the equivalent of power plants for the digital age, generating the intelligence that will run future businesses, then the company that controls the design and production of those generators holds an astonishing amount of leverage. They effectively control the pace of global innovation.
It is a level of influence that is almost unprecedented in modern history. And as this technology continues to evolve and reshape the global economy, it leaves us with a critical question for you to ponder. We want you to think about all the interconnected pieces we've discussed today: the parallel processing, the custom chips, the CUDA software, and the memory constraints.
Thank you so much for joining us for this deep dive.
Do you think NVIDIA's biggest advantage is hardware, software, or the ecosystem around both?